Hello, everyone! Today, we begin a fascinating chapter called Parallel and Intersecting Lines. Have you ever watched a railway track disappear into the distance? From where you stand, the two rails seem to move closer and closer together, yet they never actually meet. Now, look around your classroom. The opposite edges of your notebook, the sides of a window, the floor tiles beneath your feet, all follow the same hidden order. These are not random arrangements. They are examples of geometry at work. Long before engineers design a bridge or architects draw a building, they rely on the precise relationships between lines. Let's uncover these ideas with nothing more than a square sheet of paper. Fold it a few different ways, then unfold it and observe the creases. Some creases intersect, while others remain side by side. From this simple activity emerge two of geometry's most important ideas, intersecting lines and parallel lines. Every mathematical discovery begins with careful observation. As patterns emerge, logical reasoning helps us explain why those patterns must always be true. Now, focus on two creases that cross each other. They intersect at exactly one point, creating four angles. Imagine one of those angles measures 120 degrees. Can you determine the remaining angles without measuring them? Yes, because geometry depends on reasoning, not guesswork. Two neighboring angles together form a straight angle, so their sum is always 180 degrees. If one angle is 120 degrees, the next must be 60 degrees. Continue this reasoning around the intersection, and another elegant relationship appears. The angles opposite each other are always equal. The neighboring angles are called linear pairs, while the opposite ones are known as vertically opposite angles. In mathematics, recognizing a pattern is only the beginning. A relationship becomes a mathematical truth only after it has been justified through logical reasoning. Such a logical justification is called a proof. Now, imagine a special case in which all four angles formed by two intersecting lines are equal. Since the angles around a point total 360 degrees, each angle must measure 90 degrees. These lines are called perpendicular lines. From door frames and floor tiles to bridges and buildings, perpendicular lines provide the accuracy and stability on which countless structures depend. Next, consider the opposite edges of your notebook or the rails of a railway track. These lines always remain the same distance apart and never meet, however far they are extended. Such lines are called parallel lines. Through simple paper folding activities, we can not only observe these relationships, but also create parallel and perpendicular lines ourselves. Mathematicians represent these relationships using standard symbols, allowing geometric diagrams to be understood anywhere in the world. Now, let a third line cross a pair of parallel lines. This line is called a transversal, and it creates 8 angles. At first, they may seem unrelated, but a remarkable pattern soon emerges. Angles and matching positions, called corresponding angles, are equal. Another pair, known as alternate angles, are also equal. Meanwhile, the interior angles on the same side of the transversal always add up to 180 degrees. These relationships become powerful tests for parallel lines. If the corresponding angles are equal, we can conclude that the two lines are parallel without extending them forever. The very same ideas also allow us to construct perfectly parallel lines using a ruler, a set square, or even paper folding.